Hello everyone, thank you very much for joining this new episode of the Software Architecture Fundamental series. We're going to continue today our discussion with software-oriented architectures and we'll focus mainly on the concerns we have with this kind of architectural style. In the previous episode, we discussed about the benefits and the concerns and what software-oriented architecture is, and we compared it with the monolithic architectural style. And now we will take the concerns only, and we will shortly discuss the concerns, so that in the next episodes we can take the concerns one by one and even prove how to use different technologies from the Java ecosystem to solve those concerns. So if you're watching the event live, don't forget that you have the possibility to write me messages in the live chat. I moved my mic closer. I hope that this takes out the noise, which is probably from my notebook. And if you are not watching the event live, of course, you can still ask me questions in the comment section. You can find me on Twitter and LinkedIn. We can discuss there as well, and I will try, of course, to answer all your questions in the next episodes. So this is basically the way we're gonna start. Now I'm just going to share you my screen as usual, and you can see already what we discussed in the previous episode. Again, we discussed about software-oriented architectures and we compared them with the monolithic architectural style. You remember that when we discuss about software-oriented architecture, the functionalities, the responsibilities are split apart in different applications, while in a monolithic approach you had them all together in the same process. And of course we gained some benefits from choosing these architectural but we also have different concerns, so it's only a compromise. Remember, it's always only a compromise. The monolithic architectural style is not bad. Software-oriented architecture and microservices that we will discuss later, which is a way of implementing software-oriented architectures, is also not a silver bullet. So never consider that this architectural style one is better than another in all the situation. It's always depending on the case. Now you should be able to see the benefits and concerns we listed, and in the case of concerns we enumerated here that now, because the services that implement the responsibilities are apart, one of the problems is of course the communication, because now they have to communicate over the network. And remember that one of the rules of thumb you need to know is that the network is never 100% reliable. So you could never think that there will be no case in which the communication will fail between the services. There is always a chance that will happen. And then we have potentially problems of consistency of the data, because as we will discuss later, you might have multiple databases. Especially you will see when we discuss about the microservices architecture, that implies the persistency layer, which is the databases layer, being separated as well per responsibility, which means that each service has its own database, and there is where we might have cases where data might become inconsistent, because for example the communication could fail and one of the databases could store some data while the other one didn't store the data. So now we are forced to think about something like distributed transactions, which is one of the possibilities of solving this issue, which we will discuss. We see that the overall deployment is more complex, because now even if you take all the services, if you take the services individually, you will have the possibility of deploying each one, and that's easier from a service point of view, but in case of the full deployment, then it's a little bit more difficult, so you need to have some orchestration. Thanks Ajir for recommending me, but for the moment we have to discuss the theory trust me, practice without the theory is not possible. And also the things that we discuss here, which are architectural stuff, it's a little bit less easy to implement them in a simple example, but of course I will try to implement some examples for everything that we discuss. So for example, when we will discuss the communication over the network, we will implement also in one of the next episodes a circuit breaker, so you can see how to use different technologies from the Java ecosystem. Again, I use them from the Java ecosystem because I am a Java developer, but you will see how to apply this with specific technologies. Don't worry, because I will go to practical stuff as well, but in this stream indeed you will also have plenty of theory, because it's not possible otherwise. So I hope you understand that. So now the communication over the network is one of the things. The consistent data overall deployment is more complex, and you will see that there are some other concerns as well, like when you have a client, for example, and you have multiple services, sometimes the question is which is the service the client should call. So when you have, say, 100 of services, and you have a mobile application or a web application representing your client needs to have one service to whom it discusses. It cannot simply spread the requests to different services, because that would be too difficult to manage from multiple points of view, from the deployment point of view, from the maintainability point of view, from the debugging point of view. So you have to find ways, patterns to use to simplify these aspects. So you see, when you separate the responsibilities, it brings lots of benefits, but it as well brings lots of concerns. And now let's discuss these concerns one by one, because that's the point of today's video, discussing the concerns that occur when you have multiple services. So I will take the first one, which is the communication over the network. And I think this one is pretty clear. What happens now is that when you had all the pieces together in the same process, then there was no problem of the functionality called in my diagram here F2 to call F3, because it was inside the same process. So that was a 100% reliability. But now that you split them apart, you have to communicate over the network. So what could happen is that at some point the communication fails between the two. So which are the things we need to note? And I created a separate document here where I will note the concerns, and then I will below each concern put some points, some notes of the things we could use and what can we do to simplify or to minimize that concern, same as we did with the monolithical approach. So that, for example, some of the points again we'll even be able to use practically in the next episodes. Again, thank you very much, and no worries for everyone. I will provide both theory and practice. This channel is for both theoretical approaches and practical approaches, so you will get everything from this from my side. I promise you will get both theory and practice. But of course there should be at a time, so I cannot do both of them at the same time. Now we have again communication over the communication between the services. So I will note here communication. Each service implements a functionality, so it's clear that we have a problem now because they have to communicate. They communicate over the network. So I will state here over the network, which is not 100% reliable. And now what can we do? So first of all, I'd like to mention that we have multiple ways in which we can implement the communication between the services. And the most frequently encountered way today is using an RPC, which is remote procedure call. So this is remote procedure call approach. And this is again a way to design the communication where one of the sides is the client and the other one becomes the server, which means that one of the sides sends requests and then the other one sends back responses. And we have plenty of ways in which we practically implement this. So in practice, we use in the very old times, but I won't go into details with that one, we had Corba, and then it's been implemented in Java with RMI, which is states from remote method invocation. This is a very old as well. You will only find it in legacy applications mostly, so very legacy applications. And then we have, of course, web services. And in the web services category here we have both the SOAP implementations, all the SOAP implementations. There are again multiple SOAP implementations. Is SOAP RPC, which of course RPC stands from remote procedure call. It's JXB, it's the WS. So all the fashions in which SOAP has been implemented, and SOAP is also becoming old, and again I do already consider it legacy as well. And we also have all the kind of RESTful implementations, including here the you can consider it a layer over REST GraphQL, which is also which we can also classify here. Somebody, Marcy, did you use protobuf? No, I'm not sure what that is, so sorry, not something I have used, but I will note it down and I will check it out, because that's a way I can also learn from you guys. Thank you very much. So we have SOAP, REST, GraphQL. Let's go further. What else do we have in terms of communication? We have messaging. So messaging, and here is where I will add the message brokers. And in this category we can enumerate, for example, JMS. And here we also have recently Kafka, which is very tends to become, especially in microservices architecture, a trend. So I will say this is already a trend in implementing communication between microservices, and I will basically explain why actually Kafka is so nice when you have services and you implement the communication between services, especially if they have to communicate within the same cluster. You using a messaging approach and using Kafka is quite a good way of implementing the communication and taking out some of those concerns. But of course, you see, we have different ways in which the processes can communicate, and I basically only enumerated the decent ones, which are I would call decent architectural ways in which the process communicate. Architecture from historically point of view, from the oldest maybe to the newest, but I have to mention as well gRPC. Okay, yes, gRPC is as well here, so let's put it here somewhere. So I will add a new one in the RPC. Yeah, that's a good point. I forgot about gRPC. So here as well, thank you very much. Cool. So where was I? Yeah, there are some ways that I've seen, but I disagree completely with, like, for example, I don't know, sharing data through a specific file. So I've seen different ways in which processes may communicate, like sharing files on FTP server, SFTP server. That's of course a way you can implement communication, but it's not something that I would ever recommend. So if I would recommend someone implement something, I would go today, of course, with basically maybe REST, GraphQL, or gRPC in this case. And if it goes in terms of messaging, sharing a file over an FTP is not a good choice, but you can always relate to a streaming and the broker approach like Kafka. Now, what's the difference between RPC and messaging? Now we don't think in terms of technologies. I don't want you to think now in terms of Kafka or Corba or gRPC. I want you to think in terms of what basically the RPC concerns are and what the messaging concerns are, and what do we solve with one or the other. So let's take out for the moment and don't focus on the dashes here, the points here, which are basically ways of implementing RPC or ways of implementing messaging, and let's think about RPC and messaging in general as the two main categories in which we implement communication. And let's see where we encounter today implementations of communication between services using remote procedure calls, and where we use messaging and why. So one of the reasons you will see RPC used mainly is because of its simplicity. It's very easy to implement remote procedure calls. Now today, basically, in most cases I would say from all the presented alternatives, you will maybe see the REST services being used. So when people think about communication between RPC between services in an RPC style, in most cases they think about REST. And then of course we might still have some SOAP implementations which probably become a legacy or are already legacy. I don't talk anymore about RMI and Corba, which are very old. And then on the other side, we still see some new implementations using GraphQL or gRPC. But if you analyze all the possible cases, you will see that maybe in more than 80% of the projects, REST and RESTful services are the way to go. That's why you also see that REST is so much discussed in different books and in different articles, tutorials, and people don't necessarily go too much into details on GraphQL, for example, or gRPC, or if they do that, they do specifically because they want to discuss GraphQL. That's because REST is somehow the convention, so it's the most in the most cases. But what's wrong with these RPC calls is that the RPC calls in general, they are blocking. So when we think about using any kind of RPC way, the first potentially a concern, a problem with using a remote procedure call is that the client needs to wait for the server to finish a specific request, finish processing a specific request, and then deliver back a response. So that's one of the things. So now most of my students, when they hear my explanation about the RPC being blocking, they instantaneously, and that's a really good point, I hope you also had it in mind, they instantaneously ask me, but can't we just make them asynchronous? So for example, it's very easy in a Spring application and in Java applications in general, no matter what kind of framework you use, you just have somehow an async annotation, and you can place that async annotation over the endpoint directly or over a service method, and that means that automatically the framework will start executing that piece of logic on a different thread. So that's a good point actually, so the async. But mind that doesn't mean that by using async we change the RESTful endpoints and we make them non-blocking. Is just that the response will be delivered faster because the main thread that is started by the request, the HTTP request, ends instantaneously just because the full logic will be then executed on a different thread. So from the server point of view, from the client server point of view, even if you use async, the endpoint itself and the REST endpoint and the web services, the RPC implementation, whatever you want to tell it, it's still blocking. But it's just a way to simply throw some task that you want to be executed and allow the server instantaneously respond to the client so that the client doesn't need to wait for that specific task to be executed. But at the same time, by using the async, you of course don't have the privilege of knowing if that specific task executed up to the end correctly. So you can't always use an asynchronous approach, because in most cases you actually want to see what happened. The client needs to know what happened with the functionality they launched on the server. So they need back, for example, a status and sometimes even a response of that processing that happened. And being blocking means that you can't actually execute in this way. First of all, you can't execute something that takes a very long time, because if you try executing something that takes a long time, you will get a timeout. Well, even if you don't get a timeout because you configure your server not to deliver a timeout, which is not a good approach, that I will explain why not having timeouts is not good, but it's still, you can't do that anytime. You can't just keep the functionality blocked between two applications. But anyway, in a decent configuration, you have a timeout that when it's reached, simply the client assumes that something didn't went well on the server side. So it considers it's a problem and it displays a message, or depending on what that client is, it processes somehow the error. So you need to have a timeout, and you cannot implement functionalities that take a very long time. Then a second thing to take into consideration is that you cannot spam the server. So you cannot simply just call the same endpoint too many times, because the server then will get out of resources. And here I'd like to make a parallel and refer for the moment only to what we call standard web applications. So let me add a short note here and say we discuss about standard web apps, because in the future I would like to discuss something that's called a reactive approach. And with the reactive approach, the things are a little bit different, but they are different enough for us to treat them separately. I cannot just take the two approaches now and discuss them, because the reactive approach is complex enough to require its own discussion separately. So allow me to just say now we discuss standard web applications, and because I want to state what standard web applications are, they are simply applications that get the request, and for each HTTP request they spin up a new thread on the server side, and that thread is dedicated to that HTTP request. So that's what we called a thread per request architecture design. So it's when you have an HTTP request, you have a dedicated thread specifically for that request, which is good from some points of view. It's simple. It's easy because you always have on the same thread you know that on the same thread you always process the same HTTP request, but at the same time it consumes a lot of memory, and if you try to spam the server by calling an endpoint or multiple endpoints repetitively, then whenever you call that specific endpoint, you have to be aware that you always create a new thread on the server side, which in turns consumes a lot of memory and processing power as well. So we don't want, and we cannot do that indefinitely. A short-term solution for allowing more requests to a server, more RPC requests, and avoid spamming the server is, of course, doing that horizontally scaling. If you don't remember, in the past episodes we discussed about what horizontally and vertical scaling is. In case of horizontally scaling an application, you simply create or spin up more instances of the same application that are running on different hardware, so that you can allocate multiple resources and your application can serve multiple requests. But you still cannot do that indefinitely because it would cost too much money at some point. I mean, if you would have the opportunity, of course, to just spin up the application as many times as you'd like, maybe you would be able to do that. But as you will see, you have to allocate resources. If you have your own data center, then you will need those resources, which are at some point will end. And if you use a cloud solution, because cloud is also one of the things we'd like to discuss during this stream in one of the next episodes, that will become too costly. So a cloud solution like Azure or AWS, if you simply just allow your application to spin up a lot of instances, then the more instances you spin up, the costly your service becomes, and at some point your application will be so costly that it won't be profitable anymore. So then remember that we build applications, but we don't build them for fun. In general, they have to solve a business requirement, and they have to solve it in an economic way. So one of the maybe most important things we have to think about when we implement applications, especially as architects, is our application to be profitable. And that means at some point you cannot simply just spin up, horizontally scale as many instances as you'd like. So with RPC calls, they are blocking, they cause timeouts if the server cannot respond, or if the network fails, because again the communication might fail between the applications, and at some point you might spam enough the service to put the service down, because at some point you will not be able to scale it anymore, so it won't be able to actually serve all the requests, and you can at some point you can even slow it completely, or even make it crash because of that. So it's a problem with the RPC calls. So they are very simple. Their advantage is that implementing a REST endpoint today in probably any application framework, at least in Java. I don't, theoretically architecture is agnostic to the technology, but I will speak in Java examples because it's my specialty. But implementing REST endpoints is very, very easy. It's only adding an annotation or a few annotations, and mainly any beginner starts today. When you start learning Spring, when you start learning Spring, you first of all start by learning how to implement a REST endpoint. So I'm not sure, Sajid, if that's a question, but yes, Spring Web Flux is the dependency we use for implementing reactive applications with Spring, and that's something I will detail. Now we discuss standard web apps because we have to take them one by one, but reactive is one of the architectural styles we will discuss in the next episode. And at that point, I will probably even do a comparison for you between a standard and the web application implemented with Spring, and you will see that what the difference is from the implementation point of view. What and when can we use RPC calls? Well, you see that RPC calls are still used pretty much because of their simplicity. They are very fast. They need let's spare not much of your time for implementing them, but at some point you might have situations where you might have some kind of functionality that it takes time. You might have some kind of processing that you need to trigger, and it takes time. So what do you do in that case? If you have a situation where one service has to trigger another one, and the second one has to process something for, say, 15 minutes. It might be even more, but it's enough if you have 15 minutes, then you already cannot use anymore an RPC call. What do you do if you have to exchange a lot of data? That's another question. So maybe we need to write these concerns here with the RPC. So the concerns being what do you do if, okay, say what if, and what if you need to call a long task? And when I say a long task, I refer to time. It takes 15 minutes. Then of course you cannot have an RPC call anymore. You cannot have a REST endpoint just calling that functionality and blocking the client that expects for that task. What if you need to send a large amount of data? So that's another problem. If you have a large amount of data, again, using an RPC call, like for example a REST endpoint, it's not doable anymore. So that's another problem. And the third one, what if you have to call that specific functionality frequently? So what if you need to call frequently call, I should have said. A specific functionality. So with these three concerns, when you have something like that, it's definitely that an RPC call doesn't work anymore because of the way the remote procedure calls work in general. So with these three bullets here, you need to think about something else. Webhooks, yes, I will discuss webhooks as well, but again in a later episode, so not now. And if you have this situation, so you already have to think about using some kind of a messaging approach. The RPC approach, I really love it in terms of simplicity, and is the first I choose when I have to implement something like a call where, especially if I don't have a problem with what happens if the network goes down. So for example, if I have a web page and I need to call the backend, then with a web page and having a backend I have to call, I'm sure that first of all I cannot call long tasks anyway, because you cannot have in a graphical interface something where the user clicks on a button and they wait more than a couple of seconds at most for that. So I'm sure that when I implement something like that, I won't have a problem. I'm sure that I won't send a large amount of data. If I'm thinking about a large amount of data, then I still implement, like if I have to upload the file, I still implement a multi-part way of sending the data in chunks, and I create a nice upload functionality, and I don't have to basically have a very large communication that needs to send via one call a large amount of data. And I'm definitely sure that I don't have a case where I frequently call a task. By the way, and I want to say it because it's related to what we discussed now, in web applications I sometimes saw that polling approach for updating the web application. Do avoid that. So if you have some kind of functionality on your web interface, and you need to you have this requirement that you need to keep your data updated every 5 seconds. So it's the worst case you can implement is to poll the data like every 5 seconds, call the endpoint on the backend. That's going to be part of what you need if you want to frequently call a task. And that is something should never happen from a graphical user interface. So polling is not a good choice. In general, it's not a good choice, neither in other cases. But I've seen it lately more and more often happening that developers implement polling on the graphical interface. Say the web page calls a specific endpoints every 5 seconds. Instead of doing so, do it the other way around. Make the backend notify the front end whenever it's needed, because in some cases, during a long period of time, it's not even the interface doesn't even update anything. You just poll and get the same information again and again from the server side. And now using a cache for that is still also not a good choice, because we will discuss caches in a separate video. I won't now give you a lot of more details, but for now I'd like you just to tell you this lesson I learned over time, that polling in general is not a good choice. For example, in case of front and back end, you can use a WebSocket perfectly. Yes, I now you are faster than me, Otto. You are totally right. So yes, indeed, one of the choices here, probably the best solution, is using a WebSocket in this case. So a WebSocket allows you notify the front end from the back end side only when you have something to display, something to update on the front end, and that's a much better choice than having implementing the polling approach. So this is what I teach you. Of course, it's my opinion, and it's your right to have your own. But in my experience, and I will try to share you my experience here, I don't want to say that I'm all everything, I know everything, and I'm all knowledgeable. But in my experience, polling is not a good approach, and I prefer using a WebSocket instead, a WebSocket approach instead, when I have to implement something like that. So that's why, and now I'm going back to where I started the subject from, that's why I always consider an RPC approach from the front end to the back end usually a good choice. It gives me everything I need. It gives me simplicity. I can implement it using REST or GraphQL or gRPC, but yeah, the idea is it gives me simplicity. Having an async, I have the possibility to do async calls if I really need that, but I know that I'm not going to be in a problem just because I know that it's simply by the means of the web interface. By requirements, I will never have, or I should never have, long tasks. I should never have large amounts of data, and I should never have frequently calls. So it fits perfectly to an RPC. But that's not the case when you have two different services in the backend. And now, I mean, having two different services, this is the backend side. Okay, so in the backend side now, because we are not using a monolithic approach, we have multiple services, and the services need to communicate one to the other. So here it's where we cannot say anymore that We won't have situations where we have to exchange a large amount of data, because we will. We will have situations where the requirement asks us to have frequent calls. We will as well have situations where some task is longer. So what do we do in such a scenario? So of course, in such a scenario, you shouldn't use an RPC approach anymore. The solution is quitting using RPCs. You use an RPC approach like a REST endpoint when it fits, but when it doesn't fit, then you can't use an RPC call anymore. You have to go to something else. And probably the solution, the alternative, is using messaging. So what is messaging and how it looks like, and why is it a better approach, or the approach to use, maybe to say, when you have these what ifs where the RPC doesn't work anymore. First of all, let me introduce you shortly to what messaging and the message broker approach is. So in case of a message broker approach, you have the two services that have to communicate one to the other, okay? So you have the two services. I will call it service A, and this is simply a service in our service-oriented architecture functionality. This is service A, and it simply implements a responsibility, and it has to communicate with service B. And you are in such a scenario where you either have to do frequent calls, or you have to exchange a large amount of data, or you have to call a long task, or maybe all of them all together, because why not? It can be possible. So what do you do in such a case where, of course, a direct communication between A and B doesn't work anymore? Instead, what happens is that we add in between the services what we call a separate service that we call a message broker. And an example of a message broker could be Kafka, that we will discuss in one of the next episodes. And also it can be, for example, ActiveMQ, which is a JMS implementation, or it could be RabbitMQ, AMQP implementation. We will discuss these kinds of services later, but for now, just remember it's a service that only has the responsibility of storing messages. So this is, I will represent it with a dotted line. This is what I call my message broker. So some questions. Is it fine to use both messaging and RPCs in the same application for different tasks? So how I work in, it's a really good question, Christian. It's a really good question, because the answer is yes and no. And let me explain. So what I do, I usually prefer to have the same approach if possible. So if I can keep only using RPC in a system, then I do use only RPC. And if I can, for example, only use messaging, I do only use messaging for the simplicity of the application design. So I prefer simplicity, but there are also cases in which I can't do that, and in which I have to use both. And I'm always when I'm thinking of from the technical architecture point of view, one of the things I prefer to keep is simplicity, but at the same time I'm always open to compromises. Remember that in software development in general, whether it's development, architecture, or deployment, or some other area of software, it will always be about compromises. So I got situations and I accept situations of having them mixed if it really makes sense. But what can happen is that you can, if you correctly find the borders in your implementation, and when we will discuss DDD approaches for finding the borders, you will see better what I mean by that. You will see that there are cases where you can, for example, use one of the communication like messaging only inside one of the borders, and then it can be RPC on another border of the system, and that way you mix them where you need them, but at the same time you have an explicit border that allows you see better and not make your architecture more difficult to understand. So that's my overview on that. And then for the second question, if I go for messaging, should I only use it? I think I replied that, and you can use both, yes, but it's an art, so you have to be very careful with the next episodes. And if you stay with me here, you will learn a lot of things from my experience and the way I'm thinking when choosing to use the communication. So now my plan is at this beginning of the stream, the first episodes, I'm showing you the problems, the architectural styles, and then we will go deeper into things, and we will take them one by one, and you will see that all the things that we discussed, they link one to the other. Super. So now going back, I basically was representing here my message broker with a dotted line, and I will say MB from message broker, whatever that implementation is, because we don't care, but it's our message brokers. The message broker, basically, its responsibility is get the tasks in the shape of a message, of messages, and then we create by this what we call a producer consumer. It will either be a producer consumer or so producer subscriber approach, but the idea from now, I don't want to go into details because I will go at the moment we take this separately. But the idea is that one of the services will add a task, so it's called a message broker because A sends a message to the broker. The broker has its own responsibility to get the message and make sure that it places it into classifies it somehow so that the right other service can consume it. And while A, in our case, adds the task, B is a service that we call the consumer, and B consumes that message. And I'm actually now you're probably wondering, okay, and why is this better for the what ifs we have here? Why, when we have separation using a third service, this message broker, is it better and it solves problems like calling a long task, for example? Because instead of having A going directly to B and asking B to execute a specific task, we will have A only telling B by putting a message in the message broker that they have to execute the task, but B will take the task and will execute the task only when it can. So, for example, if B now doesn't have enough resources to evaluate that message, the message will remain in a queue in the message broker, and the other service will take the message and execute the task that's represented by that message only when B has enough resources to do that. So we'll see is basically imagine that instead of having you are kind of you just imagine you work somewhere and in a department, and you have to answer to calls from specific other colleagues from other departments, and imagine they all just come to you one by one, and they wait for you, they just stay behind your back and they wait for you until you solve their task, and they make a queue behind you and you have to solve them, and they also stay there and they watch you solving their task. That is kind of an RPC. So at some point, if you have too many colleagues asking for different things to you, you will basically get overwhelmed and you will not be able to solve anymore. You will get stressed, you will burn out because you cannot solve anymore the tasks that you are given. And now think the other way. Instead of having those colleagues stay by your back, they simply send you an email, and you get the email and you have the opportunity to solve that email whenever you have time to solve it, and then you simply reply to that email that you have solved the problem, but nobody basically stays by your side while you are solving their problem. So the messaging approach is better because basically the messages just stay in the queue and they are taken and they are executed when the service, the specific service has the needed resources to solve that task. So does not it require more time to communicate between A and B since we have a middleman? Yes, it does require, and it also adds more complexity, and that's of course the disadvantage from RPC, because we started by saying that an RPC approach is better because of its simplicity. Now going to the messaging, we solve some of the problems that we have with the RPC, but as anything else in software development, you will have to make other compromises because there is no perfect solution. So exactly as you have observed, Otto, this has first of all the disadvantage of having of requiring more time for communication, and then the disadvantage that I didn't state here, at least not in my diagram, is that when B needs to, if it needs to reply to A, because what if A needs to be notified when the task happens? So A simply adds a task, okay? It adds a task to the message broker. My star here is the task, and it's added to the message broker. When A sends the task in the message broker, they basically don't know what happens with the task anymore. They are completely decoupled by what service, so by who is actually solving the task. A and B, then they don't know each other here. A simply adds a message in the message broker, B consumes it, but A doesn't know who B is, B doesn't know who A is. It's a complete decoupling of the services, which can be an advantage, but in this case I will refer to the disadvantage of not having a direct reply from when the task is completed. And if that is something that needs to be implemented, then the only way to implement this with the message broker approach is when B takes the task and it completes the task, it has to itself put back that completed task or a response to the completed task in the message broker and make sure that we configure A to consume that specific response from B. So what's the problem? Of course, the complexity you add to this configuration, because how we do that usually in a message broker, we have we have these places where the tasks go, and we call these places destinations. And the destination you will see depending on the approach. If it's a JMS approach, for example, you have two possible destination types. They are called queues and topics. And we don't really care now if it's a queue or a topic, but say it's a queue, then you will have to design one queue that gets the messages from A and B consumes from this queue, and then you will basically have a separate queue where you will have to make the opposite, to configure the opposite, to configure B to be the producer in this queue and A to be the consumer. So with that being said, in this case, A will basically and let me represent this with an arrow, it will basically put something here, and then from here B consumes the message, and then you will have a second queue where you have the opposite. B will, when it finishes the task, will add a message, and then A consumes the response. And then of course we have other problems as well, is what happens if B fails. And we have to implement an even more complex logic, because you will have to take into consideration the failure and specific messages that have to be delivered also when something fails. So you see, depending on what you have to do, and depending on basically on the requirements you have, your architecture here might become very complex. So that's why, as I said at the beginning of today's discussion, that's why in most cases we start by using RPCs, and you see REST and GraphQL and gRPC, and of course especially REST, but in general we use RPC ways of communicating between services as a first option, because if it's possible, so if the requirements you have can be solved with RPC, then go with RPC, because it's much simpler. If we don't have that opportunity, you will have to go to messaging and solve the problems with what happens if we have a frequent call issue, or a large amount of data, or call a long task. But in that case, the complexity of the architecture you'll design might get very, very high. Kafka takes care of that all, but it also requires its configurations. So in order to have this, you still have to implement your topics in Kafka and the groups of consumers yourself. So it's maybe a smart tool indeed, and I don't disagree with that. I really love Kafka, but it's still much more complicated than, of course, a simple RPC where you just have a call from one service to the other. So that's basically even with a smart tool like Kafka, it's still more complicated to do some configurations. And of course, Kafka, as I will discuss in one of the next episodes, it's also very helpful, because the way it stores the data, it allows us to go back to some message and reconsume some message if you'd like to do that, and stuff like that, which can be very useful depending on what you are implementing. But let's focus now from the top of the mountain and understand when we choose from the main points, main ways of implementing our communication. And that's of course a start, and then we will dig into details, like for example how Kafka works and how can you use it, and maybe even implement an example that uses Kafka. And I don't have a lot of time to continue our discussion, so I will prefer to stop here, because what we managed to discuss now is from top of the mountain, this point here in regards to the communication over the network, and we have seen which are our main solutions of implementing the communications and when we choose one of them and why. And then in the next episode we will go further to discussing the consistency of the data, the deployment and solving complexity of the deployment, and then also we have to discuss different patterns, like in case of the communication. By the way, maybe we will continue basically with that, because we didn't end different ways to solve situations on the RPC where the communication fails. So for example, you will see that in some cases you can just use retries, and there are most frameworks actually implement out of the box retry mechanisms. You can use something that's called a circuit breaker, and circuit breakers are as well an important design pattern, architectural design pattern that you use in some cases. We have to discuss as well about the point we started with today, and that is what happens if you have a client and now we have multiple services, and introduce the simplification of communication by using a gateway application. So I think these points is what we will continue with in the next episode, and then of course continue with the data and the deployment of the applications. But the time is over, so with that being said, thanks very much again for being here with me and leaving all the questions and messages in the live chat. It's really nice to see how many people are active on this stream, and I hope to see you further in the next episodes as well, and continue our discussion with more and even more interesting things. And up to that point, thank you very much for being here, and have a great time for studying further. Cheers.